Okay, this is a probability question because it's about likelihood. It might just be a GCSE question. It could be a tree diagram. But because we're picking 8 glasses, it's not likely to be able to be done with a simple tree diagram. It's probably going to need to use the advanced ADMAS machinery. Your advanced ADMAS machinery for complicated probability questions is the binomial theorem. That is just a time saver on a tree. It is still basically the same tree method. So in a second you're going to see me kick off a tree. Just before I do that, notice that it hasn't actually asked me to calculate any probabilities, but since it asks which is more likely out of A and B, it seems to me that if I work out the probability of A and the probability of B, then I can compare them and see which is the greater. This is a classic example, by the way, of where you do all the work and then you forget to actually answer the question. The final move in my answering of question number 5 will be to say, 0.8 is more than 0.75, therefore A is more likely. Don't forget to actually look back and check that you've answered the question. So anyway, here I go. Here's the tree. So we've got eight picks. First, second, third, fourth, fifth, sixth, seventh, eighth. And it's basically defective or not. Just asking a question is a great trick. It means that all your tree diagrams are really simple. Remember, I strongly recommend just getting into the groove by doing this and starting off with just a couple of elements of the summary. I think there'll be 64 things from the summary here because 2 to the power of 8 is 64. Oh no, wait on. No, it's even bigger than that. It's 2 to the power of 8 is 2 to the power of 5 is 32, 2 to the power of 6 is 64, 2 to the power of 7 is 128. Yeah, there'll be literally 256 things in this summary, so no wonder some clever cat came up with a time saver for it. But what I'm doing now is just indicating how it would kick off. Okay, now these probabilities are all 7 over 50 for being defective and 43 over 50 for not being defective. Because it's a very large batch and they haven't actually told you how many glasses there are, you don't have to worry about any of that business of about changing 7 over 50 to 6 over 49. Because it's not actually 7 over 50, it might be 700 out of 50,000, in which case if you change it to 699 out of 49,999, it won't make hardly any difference. So the word large is giving us permission just to duplicate these, which is great because that means the probability of them all being defective is 7 over 50 to the power of 8. The probability of getting 7 defectives and then one that's fine is 7 over 50 to the power of 8 times 43 over 50. The probability of getting no defectives at all is 43 over 50 to the power of 8. So just literally 43 over 50 times by itself with a string of 8 repetitions. Okay, so now we're good to go. So what's the probability that none of them is defective? I've actually just worked out there. That's A. At least 2. Okay, so I'm going to use a time saver here because at least 2 means all these things, remember there's 256 items in the summary here, where there's 2 or more yeses. So it seems to me the fastest way for B is to say at least 2 is the same as the probability of not 0 or 1. So, what's the probability of getting one defective? There it is. It's 43 over 50 to the power of 7 times a single yes. Okay, so my strategy is to work out the probability of 0 and 1 and then subtract from 1. So the probability I want is 1 minus the probability of 0 minus the probability of 1. And I've got that already. Probability of 0 is 43 over 50 to the power of 8. And now I need the probability of 1. Now there it is, except for the fact that this is not the only way of getting a single yes in a string of no's and yeses. Spread throughout the summary, there's going to be lots more of these. How many? Well, that's what the binomial theorem is for. You can probably tell that there'll be 8 for this, but if you're not sure, if you want to know how many of these there'll be spread amongst the summary, lay down a C, take the power of this and the power of that, and transfer it there through addition. That plus that will be that. And then, for this bottom number, which you're about to type in a second, take the probability of whatever you're interested in. So I want the probability of, count the number of things whose probability you're interested in. So I want the probability of a single yes, so that's a 1 there. Now as it happens, it doesn't matter whether you put a 1 there or a 7 there. As long as one of these goes there, you'll be fine. The reason why I was doing it carefully there is I'm just trying to keep track in my mind of the fact that this predicts for you how many times amongst here you will see 43 over 50 to the power of 7 times 7 over 50 to the power of 1. So our answer is now this. And this is now literally ready to type into a calculator. And remember to type the 1 first. So apparently that turns out to be 0.299, whereas this is roughly equal to 0.311, and therefore prob of B is higher. So B is more likely. Let's just check that that makes sense, that these came out so close. Is there any reason to think these seem to me to come out to be roughly the right size. There's not a huge chance that, these glasses are okay, there's not a huge chance that they're defective. So it seems to me a decent chance that you would get none being defective, but also it seems to me a decent chance that you would get at least 2 of them being defective. Why a decent chance for at least 2 being defective? It's because you've got 8 chances to pick one that's defective. Why a decent chance that none are defective? It's because 14% is not that high a probability. What's going on now is I'm just checking that my 2 answers of 0.299 and 0.311 were sensible.